Let's take a look at the difference between zero return and home position. In order for the machine to know where the turret is, there has to be some reference point that the turret can safely move to. This position is called home position. The tool can move to home position at any time, either through program control or through a manual procedure. In either case, we would send the turret to home position through a process called zero return. This has to be done when the machine is first turned on. After that, you do not need to zero return the machine again, unless the machine is manually moved between automatic cycles. Also, if you are programming with the G50 method, you will need to zero return the tool after every tool change. The zero return position on most turning centers is a position that is furthest away from the workpiece. This would be in the full Z plus direction and the full X plus direction. If you think about it, this is also the safest position that the turret can move to. When the turret is at home position, you can index the turret and not worry about the tools indexing into the workpiece or into the chuck. On all turning centers, there are two lights on the operator panel that lets you know when the machine is at home position. Sometimes these lights are labeled origin, zero return, or home position. They will only come on when the turret is actually at home position. Even if you're just a little bit closer, 1/10 of a thousandth away from home position, the light will not be on. Even when you zero return, manually the lights will come on. During automatic mode, the lights come on at any time the tool is sent to the home position. If you watch this animation closely, you'll see when the X and Z axes arrive at home position during the machining cycle. Programming the tool to move to home position is relatively simple. The command G28 is used to specify the home position. Along with the G28 command, you will also need to specify which axes to zero return. There is one strange behavior that you must understand about the G28 command, which has to do with absolute and incremental coordinates. On the next few pages, we'll take a look at that. However, I want you to be aware there is a strange behavior when programming the zero return command with absolute coordinates. So let's take a look at that now. Let me first introduce you to two controls that are found on all CNC machines. They are the feed hold button and the cycle start button. At the bottom of the screen, towards the center, you'll see a red button. That is your feed hold. The green button is your cycle start button. Now this animation will start automatically for you, but if you want to stop it at any point, just click on the red button. To start it again, press the green button. Now, let's take a look at the G28 command. The G28 command requires that you specify which axes to zero return. The obvious and wrong way to do this is with the G28 X0 Z0 command. In absolute mode, which would be X and Z, the G28 command will first move to the coordinates specified by the X and Z values. Then the tool will move to home position. As you can see, this causes the tool to rapid through the part, which results in a crash. It is that intermediate position that the tool moves to before going to home position that confuses many beginning programmers. Watch the animation carefully and you'll see the tool come in, take a facing cut, turn the diameter, and then at that point we want to send it to home position. And that's when the G28 command would be commanded. At that point, the tool would first rapid to the position X0, Z0, which would be at the finished face of the part and at the center line of it along the X-axis. Then the tool would go to the home position. And that's where that crash came in, when it went to that intermediate position. Programming the G28 command with the U and W, specifying incremental coordinates, cures this problem. Let's take a look at that on the next slide. Now when we program the G28 command to zero return the machine to its home position, we're going to specify incremental coordinates using U and W. The command G28 U0 W0 operates just like programming it with absolute coordinates. However, when we specify the tool to go to home position, but first go to that goofy intermediate position, the tool will rapid a distance of U0 and W0, an incremental distance. And that distance of 0 means the tool actually won't move. After that intermediate position, the tool will then go directly to the home position. Watch the animation closely this time and you'll see that the tool does not rapid through the workpiece going to that absolute position of X and Z0. Instead, it just hesitates for a moment and then goes directly to the home position. Before we talk about the G28 command, I want to introduce to you one more feature of a CNC control. It's called single block. Single block allows the machine to run one command line at a time. This is very beneficial to setup people so that they can control how fast the machine runs when they are first setting up the job. We've turned that command on for the animation here. So in order to get the animation to run, you have to keep clicking on the green cycle start button below. This will step you through the program so that you can see what each command would be doing relative to the motion that's actually occurring. Now let's take a look at the G28 command here. It is the last line in this code, and you will see that it is in incremental coordinates. So when we get to the end of the program, you see G28 U0 W0, along with an MO9 to turn off the coolant. Again, you will notice that the tool does not rapid to the absolute position of X and Z0, but rather it goes straight to the home position. Very safe, very simple. This next lesson deals with how we relate the tools to program 0. As you can imagine, when the setup person puts the tools onto the turret, our program that we write has no knowledge of where that tool is in relationship to our part. Now granted, this is something that is done in the setup process. Our program has to provide a method for which the setup person can input this information. That's what we'll take a look at during this lesson. There are certain constants or consistent dimensions on a CNC machine. For example, the distance from the spindle face or chuck face to the turret face is a constant dimension. That is something that is fixed permanently into the machine. The same is true for the distance from the center line of the spindle up to the diameter of the turret. This also is a constant fixed dimension. The only way that these distances can change is if the machine tool is crashed. During a crash, the alignment of the axes, both X and Z, can be thrown out, which could shift these positions or constants. A crash occurs when the turret collides with the workpiece, chuck, or any other part of the machine. Usually this happens at full rapid speed and serious damage can occur, costing thousands of dollars and even personal injury. Crashes usually occur when an operator or setup person messes up. This is the truth of it. It is almost always due to operator error. No matter how much we want to blame the machine for crashing itself, it is almost always attributed to operator error. Now, as you can see by the graphic, when that turret rapids into the workpiece, it is tilted to one side. The graphic tends to exaggerate this a little bit. However, any amount of tilt on that turret would cause serious problems for accuracy of the machine tool. More damage can occur as well to the spindle being knocked out of alignment or damaging the spindle bearings, and the rotational position of the turret can knock the tool above or below center. All of this has to be fixed after a crash, so it is much better to fess up to a mistake than to let the problem manifest itself into poor quality workpieces later on. Getting back to our tool position and program 0 situation, we need to look again at these constants on the machine. As mentioned earlier, the constant is from the spindle face to the turret face, and from the center line of the spindle to the diameter of the turret. Those are built in and fixed to the machine. The variables start to come into play when we put a workpiece on that chuck. You will notice that the length of the workpiece would be different for each setup. Our program needs to be able to deal with this. By watching this animation, you can clearly see how that the length of the workpiece changes the variables along the z-axis. The constant remains the same, but the distance from the spindle face to program 0 on a workpiece would change depending on the length of the part, as would the distance from the face of the turret to the face of the workpiece. That would also change. Notice here that the distance from the center line of the part to the turret diameter remains constant, regardless of the diameter of the workpiece. This is a fixed dimension on the machine. The diameter of the part has nothing to do with its x-axis position in relationship to the turret while it is at home position. Now that we've seen how the length of the workpiece varies the position of program 0 in relationship to the turret face, now let's take a look at the tools and how they project away from the turret. Each tool type will project from the turret a different distance. As you know, when our program is making positioning moves, what we are actually positioning is the actual tip of the tool, not the turret face or the diameter of the turret. Our program needs to be able to deal with all of these variable tool lengths. There are two different methods of doing this. However, we'll take a look at the methods a little bit later because we need to see a little bit more about these variable dimensions and how they affect different types of tools. Drills are a unique case in that the distance from the center line of the spindle to the center line of the drill is a constant dimension. It does not change unless the machine is crashed. Regardless of what diameter the drill is, all drills fit inside of an ID tool holder. So therefore, they are located within the center of that ID tool holder. And that makes the position from the center line of the drill to the center line of the workpiece, which is program 0 for the x-axis, a constant dimension. So that is something that every programmer knows in advance. We don't even need to see the machine or make a measurement on the machine. It is always a fixed and constant dimension relative to each specific machine. Even though boring bars fit inside of an ID tool holder, there is not a fixed dimension for the setting of program 0 for boring bars. It can be easily calculated once you understand the mathematics behind this. However, what we want you to look at is the difference between the center line of the spindle and the cutting edge of the boring bar. Notice that the cutting edge of the boring bar is not along the center line of it. It is shifted off of the center line. This is what differentiates it from a drill when setting the program 0 position for this type of tool. With regard to the z-axis, a boring bar can be located anywhere along the z-axis inside of that tool block. This means that even though you may have set the job up once and measured this very accurately, 2 months from now when you reset that job up and run it again, that boring bar could easily be in a different position along the z-axis. Depending on the style of turret that your machine has, the locational position of the tool along the z-axis is usually fixed because the tool can only move up to a certain point where it bottoms out inside of a groove along the face of the turret. However, along the x-axis, that tool can be located anywhere along the x-axis, just depending on where the operator clamps it down at. So this would be something that could vary easily from setup to setup. As you can tell, we are talking an awful lot about variables and constants. There are certain things about the machine that will not change from one setup to the next. However, there are many things that can change from one setup to the next. Even if the same job is set up several months from now, many things will change, most of them relating to how far the workpiece projects from the chuck face and how far the tool projects from the turret. Here we can look at specifically the distance from program Z0 along the plus direction to the tip of the tool. That is actually what we need to tell the machine during each setup, as that is a dimension that will vary from one setup to the next. In a similar fashion, we need to be able to relate the tool's position along the x-axis to program X0 on our workpiece. Now, the first thing you must understand is that all workpieces that are mounted in the chuck will rotate about the same center line. Therefore, the distance from the center line of the part to the tip of the tool would be the same regardless of the diameter of the workpiece. Also, it should be noted that if the tool is left in the turret, going from one job to the next job, even if they're completely different parts, that dimension will not change. It can only change if the tool is actually taken out of the turret and put back in a different position. From a programmer's point of view, you do not need to know what these exact dimensions are. Fact is, you don't know what they are. The setup person will actually make these measurements with the machine tool when he performs the setup. As the programmer, your responsibility is to provide him with a way to do this. Now, there are two different ways that a CNC machine can set the program 0 position up in relationship to the tool's position while at home. The first method we will talk about is the G50 method of programming. The G50 method is the older method, however, it is standard on almost all CNC machines. The G50 command is used to tell the machine where the tool is in relationship to program 0. So therefore, we would have a command G50 with an X and a Z word. The X position would be telling the machine what diameter the tool would be cutting at if it were actually cutting while at home position. This tells the machine basically what position the tool is relative to our part. For the Z-axis, we are telling it with the G50 command the distance from the face of our workpiece, Z0, to the tip of the tool while the tool is at home position. But again, as the programmer, you don't know what these values actually will be. So you would put in some dummy numbers. For example, G50, X0, Z0. and then when the setup person goes to set up the machine, he would make the measurements and input the actual numbers into the program. In this graphic, you can easily see how these dimensions fit into our program command. Again, the G50 command tells the machine where the tool is at in relationship to program 0 on our workpiece while the tool is at home position. Now in the graphic you can see that the tool is at home position and Z0 is at the finished face of our workpiece. Not the rough face, but the finished face. And in this example you can see that the tool is 5.9834 inches away from Z0. Also, for the x-axis, you can see that if the tool were actually cutting at this position, it would be cutting an 11.705 3/10 diameter. Again, these dimensions are measured by the setup person through a procedure on the machine tool, not by the programmer. Another method of establishing program 0 with relationship to our tool positions was introduced many years ago as well, and that was through the use of the geometry offset. The geometry offset would store the tool's position in relationship to program 0 on the offset page. Now, so far you should know about where offsets. There is an identical page to the where offsets that is called the geometry offsets. And the purpose of the geometry offsets is to input these variable tool positions so that we don't have to actually alter the NC program during setup. Calling up the geometry offset is done automatically when you call up the where offset. In this example I'm showing T0707. That would call up where offset number 7 and geometry offset number 7. Programming geometry offsets is much easier because you don't have to command the G50 command. Setup it is also much easier as well because there are special features on some machines that allow for the easy measurement of these positions for the tools. When a setup person sets up a job using geometry offsets, he would go through the basic measurement procedure that we would need to do for G50s. However, the values, instead of being put into the NC program, they would be put into the geometry offset page. There is one more slight difference in that geometry offsets are usually input as negative values, as opposed to G50s, which are generally positive values. But nonetheless, if this were tool 1 on our turret, we would make the measurement just as we did with the G50 procedure, and you would see that we would put in x of minus 11.7053 for our x-axis on tool 1, and z minus 5.9834 for our z-axis geometry offset. The procedure for measuring the program 0 positions for each tool is discussed in a setup class for CNCs. You may have noticed that with the G50 method, the setup person would have to actually change the CNC program. Depending on how your company is structured, this may or may not be important. However, with the geometry offset method, the setup person only needs to change the offsets in the offset page. When you think about it, the program should contain information that is constant from one setup to the next, information that does not change. On the offset page, that is where information that is variable from one setup to the next setup should be put. Besides being easier to program, the geometry offset method is superior in performance as well. This has to do with the different ways these commands work. Let's take a look at that now. When using the G50 method of programming, you must always have the tool positioned at home position when the cycle starts. If you don't do this, the machine will crash. Now there are several different ways that the machine could be not at home position. One example would be if the program did not send the tool to home position. Another possibility is if during the cycle or at the end of the cycle the setup person or operator needed to maintain the tooling. When this happens, the setup person oftentimes will jog the turret closer to the door of the machine for easy access to the tool. They then change the insert, and if they forget to zero return it, the tool will end up being several inches closer to the part than is expected by the machine. Now if you watch this animation, you will see it first go through, face the workpiece off, turn the diameter of the part, and then go back to the home position. Then, for demonstration purposes, we move the tool to the left several inches relative to the workpiece, which means that the tool is now several inches closer to the part than the machine thinks it is, because the G50 command is telling it that the tool is 5 inches away from the part. Now when the operator restarts the cycle, the tool will be several inches closer to the chuck. The machine thinks it's several inches further away from the chuck, and when it's told to go to its first position, it's going to continue to rapid to the left and most probably crash into either the workpiece or the chuck, as in this example. This type of crash is very serious and can cause thousands of dollars of damage to the machine, and the potential for personal injury is very great. So mistakes at this point cannot be afforded. The whole problem with the G50 command at this point is that it assumes that the setup person and or the program will always have the tool at home position when the command is executed. If it is not at home position, it could only be moved closer toward the workpiece, either manually or accidentally by the program, which means that a crash will almost certainly result. Now again, so that you understand, the G50 command will always assume the tool is where it's supposed to be, and in most cases this is home position. If the setup person or operator, or even if the program accidentally did not send the tool to that home position and the cycle is restarted, the tool will almost certainly crash. Take a look at this graphic, and what we are showing is that manual shift movement that will show again in the next slide. Now this time I want you to watch the animation very closely. As was before, the tool will go through, face off the part, and turn the diameter. Then it will stop at home position. There will be a manual shift. Then the tool will take off again on the second cycle, and at that point it crashes into the front of the chuck. In this example, we are moving the tool approximately 4 inches closer to the part than the G50 command is specifying. So when the G50 command executes, the machine thinks the tool is 5.9834 inches away from the front of the part, when in reality the tool is only 1 inch away. This will certainly result in a crash, and this is what setup people and operators cannot do. At every single time that that tool is manually moved, it must be returned to home position before the cycle can start. Now there are certain programming techniques that we can use to ensure that that happens, but there is no guarantee that the operator or setup person cannot mess up during this manual intervention with the machine. The geometry offset method takes into account any manual shift, so we'll take a look at that in an upcoming slide. When working with geometry offsets, the exact position of the tool at the start of the cycle is not as important. The geometry offset, when activated, takes into account the current position of the tool. This means that if the tool is not at home position, the geometry offset will first look to see where the tool is, and then take that into account when it assigns the tool's position to the machine. Because of this, the tool will not crash into the part during a manual shift, or even if the program does not send the tool to home position. Because we don't have to send the tool to home position to change tools, as is the case with the G50 command, we can do something special that can save a little bit on cycle time. If you think about it, on a large machine, the time it takes to rapid from the workpiece back to home position and then index the tool and rapid back up to the part can add up to quite a bit of cycle time, especially when you look at the thousands of parts that are run on each machine. With geometry offsets, we can take a shortcut there. All we need to do is tell the tool to move away from the workpiece a safe distance on both X and Z axes so that we can index to any tool and not fear that the tool will index into the workpiece. Programmers will often estimate that their longest tool might be 4 inches, so they will move at least 6 inches away on the Z axis. Each situation is different, and obviously safety is of a concern here. However, the savings that can be obtained by just moving the tool to a safe index position as opposed to home position can add up to a tremendous amount of money over the course of an entire year. In these program examples, you can see a good comparison between using the G50 method of programming and the geometry offsets. The programs do exactly the same thing, except for in the case of the G50 program, we had to add the G50 commands. On the geometry offset program, you can see that it is a few lines shorter. Now in these examples, you can see that at the end of each tool, we have sent the tool to the home position. This is acceptable even with geometry offsets, especially on very small machines where there isn't a large distance between program 0 and home position. However, I just want you to look at the difference between the two programs. They both look identical, except for the G50 method requires those two additional G50 commands. In these two program examples, both of them using geometry offsets, however, the one on the left is sending the tool to the home position. The one on the right is sending the tool to a tool change position. In this particular example program, the programmer felt that a position of X of 8 inches and Z of 3.5 inches away from program 0 was a safe place to index to tool number 2. Now in both cases, you'll see at the end of both of these programs, we did send the tool to the home position. With geometry offsets, you can pick and choose where you want that tool to go between the tool changes. It is strictly up to the programmer's discretion. Keep in mind, however, that the setup person may want to alter these positions depending on certain circumstances that exist out on the machine that the programmer did not foresee. In this animation sequence, you can see how the program would run when moving the tool to that tool change position when we switch from tool 1 to tool number 2. After tool number 2 is finished cutting, the tool will then return to the home position. Watch this animation and try to follow along with the program. And again, I want you to keep in mind that these positions for the tool being relative to program 0 is something that the setup person has to measure during the setup with the actual machine tool. As a programmer, you have to pick which method. Now, the geometry offsets are an option on most of the machines, so you may or may not have that option. However, if you don't have it, I would recommend that you check into purchasing that option for your machine, as it is a much more contemporary and superior method of programming, as well as machine tool usage. It is much safer, it can be much faster for setup, and it allows for much greater flexibility in the long run with CNC machine tools. There is another purpose for the G50 command which has absolutely nothing to do with program 0 and tool positions. The G50 command can be used to limit the maximum RPM of the machine. This will override the machine's maximum RPM. in cases when there is an out of balance part or when using a bar feeder and the maximum RPM needs to be more closely controlled, especially when you're working with bent bar stock, which is quite common with bar feed operations. The G50S command is modal and will carry over, or in other words remain active, until another G50S command is given. In the program example below, you can see the G50S 1500 at the beginning of the program. That would limit the RPM of the machine to 1500 RPM until another G50S command is given, either raising the RPM or lowering it. Again, this is to override the machine's maximum RPM. Many machines can go up to 4, 6, even 10,000 RPM. And if you're working with large bar stock, parts that are out of balance, such as castings and forgings, or with bar feeders where you're working with a very long piece of bar stock, these particular workpieces may not be safe to run up at machine maximum RPM. It is these situations that you would want to use the G50S command to override the maximum RPM of the machine. And again, the S word in this case is always going to specify RPM. It's time once again to take another quiz. Good luck, and I hope everything works out fine for you. In general, which method is the most safe? G50 method, geometry offset method, home position method, or the zero return method? With the G50 program, the setup person enters the X and Z values into the wear offset screen, into the geometry offset screen, into the program, nowhere. The programmer enters the correct values. Home position is usually at the front finish face of the part, the back finish face of the part, the furthest X and Z plus direction the axes can move to, or front finished face and center line of the part. The command G50S 1500 limits the RPM to 1500, limits the SFM to 1500, or limits the feed rate to 1500. When using geometry offsets, the tool change position can be at any safe position including program 0, at any safe position including home position, done only at home position, or done only at program 0. Program 0 is located at the right finished face and the center line of the part, the left finished face and the center line of the part, the furthest X and Z plus distance the tool can move to. Which is the best way to program the zero return command? G28 U0W0, G28 X0 Z0, or does not matter which way. With geometry offsets, the setup person enters the X and Z values into the program next to the G50 commands, into the Where Offset screen, or into the Geometry Offset screen. The origin lights come on when the axes are at program 0, at home position, not at program 0, or not at home position. We zero return the axes to the home position or the program 0 position. When using G50s, it is best to change tools at program 0, at home position, at any safe place, including home position. Which of the zero return commands is incremental? G28 X0 Z0 or G28 U0 W0? Take a moment now to review your score. If you scored 0 to 50, review the entire lesson again. You really must have missed something. If your score is 51 to 100, just review a couple of the troubled areas where you were most concerned. If your score was 101 to 120, you did a great job. Go ahead and continue on to the next lesson. But before you do that, I need you to enter your name up above by taking the mouse and pointing to that box next to Student Name. Click the left mouse button once and then enter your name. After you have entered your name, a button will appear at the bottom of the screen that states Print Quiz Results. Go ahead and click on that button to print out your score. Good luck, and we'll see you in the next lesson.